Okay, so this is my video walkthrough of the program that I wrote. I wrote it in Python. This is a Jupyter notebook. So starting with the first class, it's just a board class, which represents the game board, I guess, and all the arrangement of the tiles. For the initialization of that class, you pass in the arrangement, which is just a two-dimensional array, three by three in this case, and the parent of the board, which defaults to none. Then we have this string representation built-in method that just basically says, hey, when you print this thing, what does it do? And as you can see, it's just going through the arrays and putting them out into a string format so that they look good when you print them. This hash is another built-in, and it's essentially makes it so that you can put a board onto a set, which makes it easier to search. And this little trick is just to convert the array of arrays into a tuple of tuples, because the tuple is immutable and can be hashed. Then we have the equals built in, which is just going to compare the given board to a board that you pass in. In this case, all it's doing is walking through the array of arrays and comparing to see that each number are in the same place. This create child method is just basically a copy method. It takes the arrangement, and then copies it exactly as it is, and the only difference being that when it creates the new board, it's passing itself in as the parent. And so this is get children, which will get all of the possible moves from the current board that you're in, and it starts by getting the location of the blank on the board, and then it gets the blank row, it gets the blank column, and then row count and column count is just the width and height of the given board. And then it's going to walk through each of these possible scenarios. The blank row -1 with the blank column, blank row +1, blank column, etc., which is moving the blank all around that it can move, as long as it stays within the parameters of the width and the length, height of the board. And if so, it creates a new child, and then it moves the blank space to the appropriate spot, depending on where you are in the loop there. Alright, this is the get location of blank, and basically it's just walking through the arrays until it finds the blank. Alright, so that's it for the actual board, maintaining the state. This is the solver class, and when we initialize it, we pass in the starting state for the board and the goal state, and then we call this solve method, and you pass in what kind of algorithm you want to run. It defaults to DFS. If you pass in BFS, it's going to do a BFS call to the BFS, and otherwise it's going to call to the DFS. Then after it gets the solution, it just creates this path array and walks up the board, that the final board will have a parent, and he'll have a parent, etc. So it walks up that parent chain, adding each of those boards to path, and then reverses that path so that you get the solution starting from the very top down to where you are to the goal. This is the DFS algorithm. You start with the fringe, which we're just representing as an array. you start with the starting board. This is explored as just a set that we're using to keep track of all the boards that we've encountered, and so we don't duplicate our work. And then we say, while the length of fringe is greater than 0, pop the top, the first, or the, in this case will be the last item off of the array. So it's basically using the array as a stack. And then we check to see if that they just popped off there is the goal. If it is, we return it. Otherwise, we add it to the explored set. Then we get the possible children for the current, and then for each of those children, we check to see if that child is in explored and make sure that it's not in explored and it's not already on the fringe. And if those two conditions are met, then we add it, append it to the fringe. Then we're going to go back to the top of the while loop and pop the next one off, and so we'll end up going deeper and deeper and deeper. The BFS algorithm is a little bit different. The logic's pretty much the same, but instead of a stack, we're using a queue, and so we're getting that from the collections namespace. We create the queue, starting again with our start state. Again, we have an explored set, and then we say, while that queue has items in it, we pop the leftmost from the queue. So we want a first in, first out. Is that right? No. Yes, first in, first out. And then we check, so we pop the first one off the queue, then we check to see if that's goal is met. If it is, we return it. Otherwise, we add to explore. And then for each child in the get children, we say if you're not explored and you're not already on the fringe, then add the child to the fringe, and then we'll pop the next one in a first in, first out method. And so then to test all this stuff, we have a starting board, which I use the what was on the assignment, and the goal, which looks like this. We create a solver, pass in starting goal. We call solution equals game.solve, and then for each step in the solution, we print the steps. So I'll go ahead and run this, and it should do the depth first search, which looks like it took 3 seconds. And then we can look and see that it started. Oh, it's pretty deep. We might actually have to. So this is where we started with the space down here. And then this is the path that it took. You can see the space is moving. And then finally, we get to 1, 2, 3, 4, 5, 6, 7, 8 with the space in the middle. Alright, so there's that. Then if we want to run the BFS method, it's much faster. As you can see, it only took it 6 moves. And so that's that. Thank you.